Okay, so cubic functions, just like any other functions, we can transform, right? So the whole point of this is to make this stuff fit data, right? So I'm going to go out, I'm going to measure some stuff, and it's going to look like kind of this shape, right? It's going to look like a, I don't know what you call it, almost like an S shape or whatever a cubic is. And I want to make that data, or I want to write an equation that fits the data. So we're going to do what we did at the beginning of the year, which is a transformation. But I want to talk to you about what some of these things are first before we do the transformations. So basically, by multiplying or adding, subtracting, there's certain things that we can do that helps with those transformations. So the parent function for a cubic is always x cubed. And then all these transformations, A, B, H, K, all those things either translate left to right, translate vertically up or down, compress or stretch horizontally. And then A can actually stretch or compress horizontally. And if A is negative, it flips it, right? Do you guys remember that from all the other functions? And so if I say x is -1, y is -1, x is negative b plus h, y is a minus k, what they're talking about is how you can take this and set it up in this equation. So if I have some sort of cubic and I identify a, b, h, and k, that gives us some information. So what we're going to do is, I guess I was going to explain, but let's just dive in. So what we want to do is identify the transformations of the parent function, x cubed, which is the parent function of the cubic, that produce the graph of the given function g of x. G of x on the same coordinate plane as f of x by applying the transformations of the reference points -1, comma 1, 0, 0, and 1, comma 1. So we're going to have two functions here, right? And so let's identify what's what. So I'm going to identify, I don't know if you guys recall this, but this is our parent function that I'm highlighting in red. Do the best you can to sketch that out. Okay. That is the parent function f of x. That is f of x is equal to x cubed. And we'll graph this on the graphing calculator so you can see it better. So now if we look at this, there's some things that are going on. So they tell us that the graph is this, right? Okay. But let's look at what's really going on. This particular part of the function, right? Well, I'm not going to tell you. I want you to kind of observe. So look at the two functions. What do you notice? Okay. Any other observations? In other words, this gray one here, this gray one is g of x, right? You guys know that? That's the transform function. This one right here. It draws a pretty straight line when I have a straight line. I wonder why it looks so ratchet when I do it the other way. All right. So there's that. All right, so let's see what the book says. So it says transformations of the graph f of x to produce the graph g of x are, there is a vertical stretch by a factor of 2. Well, we knew that, right? A equals 2. That means that it is a vertical stretch. By the way, that isn't any different than all the other translations, right? And then we have a translation, 1 unit to the right and 1 unit down. Okay? So 1 unit to the right, 1 unit down. What do you think causes that translation? Well, I know that k translates down, right? K is -1. And h is 1 unit to the right. Remember, it's the opposite direction. So if I have a negative sign here, in other words, h equals +1, k equals -1. So because h has a +1 value, that's going to be my horizontal shift to the right. Because k has a negative value, that's going to be my vertical shift down, the translation. It says, note the translation of 1 unit to the right affects only the x-coordinates, while the vertical stretch by a factor of 2 and the translation 1 unit down affects only the y-coordinates. In other words, this right here, if you want to think of this, this is what we call an inflection point, but this point right here goes down 1 over 1. Now, technically, if we were to do that here, there should be a point right here, but because we stretched it vertically, see how that changed it? And so this point here is actually going to be down here because we stretched it vertically by a factor of 2. Does that make sense? Okay. So now